Welcome to the class of material selection for mechanical design. Okay. We are going through the module 2, this is lecture number 8, and this will be the continuation of our last discussion on fracture. So, I have kept the same type part 2 here, and here instead of fracture we are going to talk about fatigue. Okay. So, as a product designer, you should always have in your hand, other than the measure modulus of elasticities and the strength, the fracture and fatigue properties, and you should always have a qualitative idea about that what is the fracture strength or fracture toughness of a material and what is the fatigue strength of a material. Particularly fatigue will be important when there is a chance that the material is undergoing stress, and that is cyclic in nature. That means the stress is having a high stress and a low stress alterations, something like this. So, if I try to look at it, that what do you mean by this? So, it is that the stress has an average value and it goes to a high value and to a low value continuously. So, you have a sigma max and you have a sigma mean value, and this is where you have the sigma average value. Okay. There are of course some rare cases, and that happens during the bending type of an applications, where the stress value may actually vary between positive and negative. Imagine that you are having a continuous bending vibrations. In such cases, the stress value can be positive and negative, vary between the two. Okay, so the properties that will be important for us will be fatigue strength, sigma f, which is the maximum cyclic stress for a specified number of cycles without failure, endurance limit sigma n, that is the stress amplitude below which the material can theoretically endure an infinite number of cycles. So, you see everywhere when we are defining fatigue, this number of cycle is also important. Okay? Number of cycle, and also another thing that we later on see, that is the frequency of cycle. Both of them also plays important role. So, the fatigue life is defined by this parameter Nf, which is the total number of cycles to failure under a specified cyclic loading condition. So, let us look into fatigue into a sort of a much more detailed way. So, how do we define first of all fatigue? Fatigue is the progressive initiation and propagation of cracks caused by cyclic or fluctuating stresses. So, you see we are not just interested that the material is undergoing a cyclic stress, okay, until and unless there is a chance that there are cracks in the material which gets energy because of these fatigue cycle, and then the cracks start to propagate and the failure happens. So, fatigue is inherently it is related with the possibility of a fracture. Okay. So, now a fatigue failure generally will have 3 stages, that is crack initiation at a stress concentrator, maybe there is a surface scratch, maybe there is a notch inclusion or weld defect. So, there the crack is initiating, and then as this cyclic loading is happening, crack is propagating, and then the final fracture when the remaining cross section can no longer sustain the load. Okay. Interestingly, a material which is apparently ductile in nature, you take for example a sort of a copper wire sample, okay, and then you do the sort of a continuous repeated cycling of it, you will see that it is going to break. Okay. So, that means that is what is happening, that first there is a crack initiation, then the crack propagates, and finally it fails like a brittle material. So, this is something that is a telltale sign of a fatigue failure. How do we quantify then fatigue? As I have shown you earlier, that maximum stress, minimum stress and stress amplitude, which is sigma max minus sigma mean by 2, these are the first important quantification of the fatigue. And the fatigue strength is the maximum cyclic stress amplitude that a material can sustain for a specified number of cycles without failure. So, always it has to come with a specified number of cycles. Every product has a specified number of cycles. Particularly it is true for aircrafts or for any transport system, but definitely for aircraft, even a simple bolt will have number of cycles up to which you can actually use it, and hence within that number of cycle, whatever is the maximum cyclic stress amplitude, that is what is going to define the fatigue strength of the material. Now, the fatigue life NF is the total number of loading cycles that a component can survive before fracture. So, if a fatigue life is 10,000 10 cube, so 1000 cycles, it has a very short life. If it is 10 to the power 5 cycles, we call it to be medium life of a sample. 10 to the power 6 cycles is long life. 10 to the power 7 to 10 to the power 9 cycles is a very long life, and if it is infinite, we say that it is well within the endurance limit. But of course, the endurance limit is true only for some metals, not for all the metals. You do not get an endurance limit for all the metals. Now, what is endurance limit? That is another important property against fatigue. It is the maximum stress amplitude below which a material can theoretically withstand an infinite number of cycles without fatigue failure. Okay? And it is primarily applied on carbon steels, low alloy steels, and some titanium alloys. We have a thumb rule that we keep this endurance limit as maximum up to 60% of the ultimate tensile strength. Okay? So, 45 to 60% and maximum up to 60% is the endurance limit. So, if your stress amplitude goes above that, then it is not going to sustain infinite number of cycles. It is going to have finite number of cycles, and then depending on the application, you can say that okay, whether it is a short life one, desirable, medium life, etc. Now, some materials do not exhibit a true endurance limit, as I told you that, for example, aluminum alloys, magnesium alloys, copper alloys, and the polymers, they do not show a proper endurance limit. Another few important factors for fatigue are low cycle, high cycle, and very high cycle fatigue. So, if the fatigue life, this NF, is between 100 to 10 to the power 4, we consider this to be a low cycle fatigue, okay, which occurs when cyclic stresses exceed the yield strength, producing significant plastic deformation in each cycle. So, the possibility of such low cycle fatigue is generally observed in turbine blades during the startup and shutdown, pressure vessels under thermal cycling, okay, nuclear reactor components, and a particular actuator which we call shape memory alloy actuator. Okay. There also the low cycle fatigue is observed. Okay. So, that is one group of fatigue possibility. The other group of fatigue possibility is high cycle fatigue. Now, before I talk about it, I want to actually show you that how we determine these fatigue strength, endurance limit, etc., and we do it with the help of something which we call Euler curve or SN curve. Okay. So, in the SN curve, what we have is that on our x axis we have the number of cycles in the log scale, and we plot the fatigue strength in the y axis. So, now if you look at it, that the fatigue strength will be, the endurance limit will be very clear if the SN diagram show this type of a shoe that a steel shows. Okay. But say for example, fiber reinforced plastic, you will never see that this is happening, it is continuously coming down. Even for aluminum also, it does not exactly saturate, it continuously sort of comes down. That is why it is not very clear the endurance limit for them, but for steel you get a distinct endurance limit. So, if this is, and this limit is, as I told you, maximum up to 0.6 of sigma u. Okay. So, that is how the SN curve, whenever we get a sample that you need to test it for fatigue, we actually obtain the SN curve, okay, the total number of cycles that we can withstand, and from that we try to get the endurance limit, etc. Now, I told you that the like low cycle fatigue, there are applications which will be high cycle fatigues. For example, the rotating shafts, okay, or the bearings or the springs, aircraft wings, or robotic gear train, or electric motor rotors, etc. So, they all have typically the fatigue cycle is greater than 10 to the power 5. So, in such cases the cyclic stress remains below the yield strength, but the deformation is essentially elastic. So, that is the difference between low cycle and high cycle fatigue. Low cycle fatigue shows plastic deformation, whereas high cycle fatigue, the deformation is elastic in nature. Now, you can also have some systems which in modern days which are actually high cycle fatigue system. Okay, that means NF is greater than 10 to the power 8. See, systems like MEMS devices, ultrasonic motors, aerospace actuators, high speed bearings, piezoelectric systems, in all such cases the type of failure can happen them is only in a high cycle fatigue, and that happens because of the presence of internal inclusions in them. So, generally they are, that is why very good for a long number of cycles, but ultimately the failure occurs, it will be because of some inclusions that will be able to sort of the sort of force the crack to propagate. Okay. Now, I will come to another important property. So, we have talked about the elasticity related properties, the strength, we have talked about the fracture, we have talked about the fatigue. Okay. However, you see in many cases, particularly for mechanical system designs, there are always some kind of a relative motion between the objects that takes place. Okay. And there are always chances of a material which is subjected to some sudden loading condition, okay, which can create a sort of a plastic deformation on the material. So, in both the cases hardness is something which is an important factor. So, if your application has repeated contact, has sliding, has indentation or abrasion, in all these cases it is important that we check the hardness of the system. You consider, for example, I just want to give you an example that you have all these gears, right, and then the gears are messing with each other, right. So, there is a repeated contact and non-contact that is happening. So, unless the gear tooths are specially hardened, they will wear, and that means the load transfer will not take place in the system. Now, if you look at the definition of hardness, it is a measure of materials resistance to plastic deformation. Okay. So, that is the way we define it. Now, what are the advantages of hardness testing? It is very simple. It is one of the simplest one in comparison to all other tests. Okay. Simple and inexpensive, and sometimes it is just a small indentation is good enough. So, you can almost consider it to be a non-destructive way. Okay. And sometimes you can actually get the hardness. It is true for some metallic systems. You can use a relationship which is known as a Tabor relationship, where you can obtain you can obtain the tensile strength SU from the hardness of the data, and vice versa. But generally we get the hardness data, and from that we actually predict what will be the tensile strength of the material, and that relationship for this Brinell hardness is given by this. So, where you have the x value which is n minus 2, and n generally varies between 2 to 2.7, and it is known as the Meyer index. So, if you know the value of x, so that is known to you, let us say, and then you have tested the HB, you should be able to predict what will be the tensile strength of the material. So, that is an advantage on top of just measuring the hardness. Now, how do we quantify hardness? Okay, there is a qualitative way that people earlier used to use, which is called the Mohs scale of hardness, which you can simply do by scratching a material with the other material, and talc is generally considered there as the softest one. So, then gypsum can be scratched with talc, and then that will be, gypsum, you can use gypsum to scratch on talc, and then of course all other materials. So, thus all the other materials are harder than talc, and that way all the materials you can arrange, and what you are going to see that this is, if this is having the lowest hardness, the maximum hardness that you can see is in diamond. Okay. So, that is why diamonds are used as indenters. Okay. And next to that is the alumina, which is used also for different types of tools, that is used for cutting, etc. Now, there are some quantitative other quantitative ways, for example, macro hardness tests and micro hardness tests. In the macro hardness tests, we have three such tests: Rockwell hardness, Brindle hardness, and Vickers hardness. And in the micro hardness, you have Knoop and the Vickers micro hardness. The difference between macro and micro is simply in terms of the diameter of indentation and the load that you are applying. Okay. So, macro hardness tests are generally done for large samples where it is the scale or the magnitude the structure is subjected to is large, whereas micro hardness tests are more important for precision engineering applications. Now, the Rockwell hardness test, so the way we define is that there is a minor load which is first applied for good contact, and then we actually use the a major load, and the depth of indentation we record through a dial gauge. Okay. And the indenter shape is typical. Rockwell hardness test is a cone shaped indenter for harder materials, or a small diameter steel ball can be pressed. So, either of them, and importantly that a minor load followed by a major load, that is F1 followed by F2, and then you check that what is the level of indentation. So, the permanent increase in depth of penetration due to the major load. So, first you apply the minor load, you know what is the depth of penetration, then you apply the major load and you see what is the permanent increase in depth of penetration, because it is a plastic deformation. And there is another parameter, it is a constant depending on form of indenter. Okay. So, HR, the Rockwell hardness number is simply E minus U, and this is done in three scales. Okay. Scale A, scale B, and scale C. And for scale A we use cone, scale B steel ball, scale C cone again. Load is also very much defined, 60 kg for scale A, 100 for scale B, and maximum for scale C, that is 150, and this is used for ferrous metals and tool steels. So, this is the Rockwell testing system. Then we have the Brindle hardness test system. This is used for metals and as well as non-metals of low to medium hardness. So, here what we do is that we do not use any cone, we use here a hardened steel ball of 10 millimeter diameter. Okay, and that is pressed to the surface of a specimen using a load of 500, 1500 or 3000 kg, and then we again measure that what is the indentation diameter. Okay. So, what we do is that we look into these indentation pattern, and we find out that what is the minimum and the maximum diameter around through different measurements at different points, and then we take the average indentation diameter, and then that average indentation diameter is known to me, the ball diameter is already known to me, the load is known to me, we should be able to calculate what is HB. Very interestingly, here also there is a thumb rule that for steel alloys the tensile strength is about 3.45 times HB, but this is just a empirical thumb rule. Now, a Vickers hardness test is the other macro hardness test. In this case, we do not use a cone or a ball, we use a square base diamond pyramid. Okay, and it has an angle of 136 degree between the opposite faces, and this is obtained by putting a load between 1 to 120 kg, and then we calculate this surface area. See, the good part here is that because it is a square base diamond, so we need really too few measurements to do calculate that what is the impression of it on the system, and then we calculate this length L, and once we know that and we know the force, we should be able to calculate what is the Vickers hardness result of the test, the hardness test. Okay, so that is the Vickers hardness test. Now, as I told you, for precision systems we use something which is called micro hardness test. Okay, and this is used in a very small area. So truly this is much more non-destructive in nature. Okay, and this is used for materials like carburized steel surface or coatings of individual phases or constituent of a material. Now, the load applied in a micro hardness test is much smaller, and hence you need an optical microscope to look into the indentation. Now, there are two types of micro hardness testing, loop hardness and Vickers micro hardness. So, loop hardness test is done generally for very brittle materials or thin sheets, and here also similar to the macro scale, a pyramidal diamond point is pressed into the polished surface of the test material, and for a specified dwell time, and then the resulting indentation is measured using a microscope. So, again you find out the length, but in this case it is 14.2 f times L square, through which you are going to get this loop hardness test, the hardness value in the loop hardness scale. So, that is what is the loop test, and another micro hardness test is a Vickers micro hardness test. Okay, so this is done for a much smaller load range, 1 to 100 gram. Okay, that is the important difference with the loop test. Now, all these actually are related to each other. Okay, so for example, Rockwell C, Rockwell A, Vickers, you can actually plot each one of them and you can transfer one to the other. And later on you can also see that you can try to visualize that in a hardness scale where the materials are. Already I told you that diamond has the topmost position, and then you have the nitride steel, cutting tools, and all of them would come below this level, and aluminum and brass will come even lower than that, and then most of the plastics will appear. Okay. So, you now know that suppose if you have to make tools, then you have to use the hardest type of material. That is why the cutting tools and all these are used with the very hard kind of materials. And then the next group will be the easily machinable steels. Okay, they have relatively good hardness, so they will have relatively less wear. And then below that is the brass and aluminum, and plastics are having the least hardness among them. So, these two properties that we have learned today, in this lecture, one is the hardness part of it, and the other is related to this system that we have talked about. The if you look at it, the the fatigue. So, fatigue and hardness, these are the two things that we have sort of discussed in this lecture. and we also know that how to select materials from the fatigue and from the hardness point of view. Okay. So, this would sort of create the basic framework for us in terms of the material choice. Further discussions we will do on some more material properties in the next lecture. Thank you.